Hi guys, in this video I am going to explore the relationship between potential difference and electric field, right? And my goal is to get you to a point where if you know the potential difference, we should be able to figure out the electric field, right? So let's start with again basics, right? Potential difference, what is it? So if there are 2 points, let's say A and B, right? The potential difference is the work done by an external force to take 1 unit charge. If I take 1 coulomb charge, if I take it from point A to point B, right, then the work done by the external force, right, is equal to my potential difference. We'll say PD, potential difference, is equal to nothing but work done by the external force, right, in this case. Right? In general, if it's not 1 coulomb charge, right, if let's say charge is Q instead of 1 coulomb, let's say charge is Q, right, in that case potential difference is going to be work done upon Q, right. This is a general formula for any charge. Okay. Now let's try to find just think about, the relationship between potential difference and electric field. Right? So let's start with a simple case. I'll take the case of a uniform electric field. Okay. So let us say there is electric field and it's uniform, and I'm drawing the electric field lines and they are pointing in the same direction and they are equidistant, right? So the field is uniform. Now let's say in this field, the field is there everywhere, right? I'm just drawing it here. The field is there throughout. Now if I take an object from point A to point B, okay? This is my A, this is my point B, and if I take an object from here to here, right? And it has got charge, let us say it has got charge Q, okay? So the question is, what will be the work done? Right? Now, the electric field here is constant. Let's say the field is E, right? So first thing is the relationship between electric field and potential difference. So think about it. The potential difference is the work done per unit charge, right? So if the work done is W, right? My potential difference V, right? Potential difference V, and I'll call it VBA, right? In this case, VBA is nothing but VB minus VA, right? So VBA is my potential difference, right? Potential difference. VBA is going to be nothing but work done upon Q. Right? This is the definition. Right? Now the question is, what is the relationship between this and E? So let's kind of explore that, right? Now, if the field is stronger, right, then more work will have to be done. Okay. Once again, if E is more, then I have to push more. Right, which means more work has to be done. So it seems like higher the electric field, higher is the potential difference. That's number one. Second thing is, I'm not doing mathematics now. I'm just trying to give you a basic idea. So first thing I observe is that electric field, the higher the electric field, right, the higher is the potential difference. Right? Number one. Number two, if I were to take the charge for a certain distance, I will do some work. If I will move the charge for a longer distance or for a bigger distance, I have to do more work, right? So again, the second intuition I get is that, when the distance, let's say D, goes up, right, then my potential difference also goes up, right? So this is kind of a just to give an intuitive feel, right? The third thing I would like you to observe is that when the field is in this direction, right? When the field is in this direction, I have to do work when I move the object in the opposite direction, right? I have to do positive work, which means the increase in potential, just listen carefully, the increase in potential difference, right, is the direction of increase of potential difference is opposite to the electric field. Once again, right? The field is in this direction, I'm moving the charge from here to here, right? Now, the direction of increase of potential difference, right, is opposite to the direction of electric field. So that's interesting, another interesting observation, right? So we'll say direction of increase, right, increase of PD, right, is opposite to electric field direction. So these are some of the observations I'm able to make without getting to hard mathematics, but I'm trying to build your intuition here, right? Now let us get a little mathematical here, right? And it's not very hard. So let's now I want to find out what is my what is my potential difference, and I want to do this mathematically. So it's fairly easy. So let's find Q is given. If I find the work done, I can find my VBA, which will be nothing but W by Q. So what is W? Here, work done W is equal to what? This is equal to, so work done is what? Work done is F dot S, if F is constant, right? Here my force will be constant because the electric field is constant. So I have to oppose electric field, so I am applying a constant force here, right? So here my W is going to be nothing but F external, right, dot displacement, right? So dot displacement, I am going to call the displacement D vector. So this would be D vector, right? So let's say this is my D vector, right? This. Okay. So this is my this is the work done, right? Now the force I am applying, what is the relationship between this force and electric field? Think about it carefully. Right? First thing is, my force, right, is opposing the push from electric field. Once again, the force I am applying is opposing and is equal and opposite to the push of the electric field. Now, how much is the force electric field applying on this? The force applied by the electric field is nothing but Q into E, correct? And we know that my force is opposite to this, right? So I can say that this electric field, right, this is equal to negative of F external, correct? I'm taking, so here E is in this, electric field is in this direction, so the electric field force will act in this direction, I'm pushing in the opposite direction, right? So my force or the external force is going to be opposite of electric field force, and by the way, direction between them is going to, sorry, the angle between them is 0, so I can just write this simply as F external, right, into D, because cos of 0 is 1, right? So now if I substitute this here, I get that, and this is I'm doing for a one-dimensional case, right? For one dimension, sign is sufficient to represent the direction, right? So here, now I can put this value here, right, and I can say that work done is nothing but F external into D, which is nothing but minus FE, so let me go step by step, F external into distance, which is nothing but minus of FE into distance, and therefore W is nothing but equal to minus, and what is FE? FE is nothing but Q into E, right? So it's going to be Q into electric field into distance, right? And therefore I can say that I can divide both sides by W, so I'll get W by Q is equal to minus ED, and what is W by Q? It's nothing but VBA, right? So we'll say, which means this is equal to also VBA, right? And what is VBA? VBA is nothing but VB minus VA, because this is the potential difference. Potential difference is the final potential minus initial potential, right? This is equal to VB minus VA, right? So now I know I can say that VB minus VA, right? And this I can now call this change in V. I'll give it a symbol delta V, right? Delta V is not a new thing. I'm just saying instead of writing this in full in long form, I'm just going to call this delta V, which is change in V. So change in V is nothing but equal to, this is nothing but equal to minus ED, minus D into E, yeah. And therefore now I can say that my electric field E is equal to minus delta V by D. So electric field is equal to negative of change in potential by distance.